We have learned about nucleophilic substitution reaction. So before we start to the discussion, let me discuss briefly with whatever we have covered in the last session. So in the last session, we have discussed about nucleophilic substitution reactions, where generally nucleophile was reacted with alkyl halide to form the product in alkyl halide. So this reaction is generally termed as nucleophilic substitution reaction. Reaction where a nucleophile reacts with alkyl halide, and that will form certain product, which is along with the formation of this halide anion. So basically, this is a reaction of nucleophile and alkyl halide to form the substituted product and leave certain group. In organic chemistry, there are major 4 types of reactions called substitution, addition, elimination, and rearrangement. This is a substitution reaction where one of the group is replaced with other group. So mechanistically, we have seen that this nucleophile will attack on electrophilic carbon along with the departure of this halide anion, and that will form certain transition state, and this will. The transition states are always drawn in a square bracket with a symbol of, let us say, double dragon. Then we have focus on free energy diagram, which is basically a kind of free energetic reaction for nucleophilic substitution reaction, SN2. 2 types of nucleophilic substitutions are there. One is called as SN1 and other is termed as basically this SN2. So with respect to that, generally we have studied about this one, that certain reactants are converted into, let us say, the products, where reactants are converting into this one. For methanolic reaction also, this already we discussed in the previous session, where nucleophilic hydroxide ion will react with methyl chloride and it will form certain transition state, and then it will form this product. With respect to stereochemistry point of view, that we have seen that nucleophilic substitution reaction, this one is basically SNAR, where certain, let us say, so this is SN2 reaction where umbrella inversion is generally possible, where somehow kind of this SN2 reaction where hydroxide ion will attack on this electrocarbonyl carbon, and that will leave this delta minus to form this transition state. So what will happen, that whatever the product is, that the product will have exactly different configuration as compared to the other one, and we will be able to see the stereochemical inversion for this configuration. So basically, this is somehow called a nucleophilic substitution reaction that we have seen in the previous session, and in this session we are going to learn majorly the reactions of alkyl halide. So preferably with respect to, let us say, what are the several factors affecting this nucleophilic substitution reaction. So that is a major objective behind this session, which we are going to learn today. So these reactions are generally, let us say, these are the reactions of alkyl halides, which basically involve SN1 and SN2. So let us say if we wish to react, what the characteristics of alkyl halides. So alkyl halides generally they have a carbon which is connected with halogen, fluorine, chlorine, bromine, and iodine. All the carbons which are present over here, they will have a partial positive charge, and the delta negative charge, which is basically this partial negative charge, is present on the head of each and every halogen ion. So that way, this F minus, delta minus, and this different substitutions can be possible. But look at to the bond dissociation energy for this carbon fluorine bond, carbon chlorine bond, carbon bromine, and carbon iodine bond. So this bond dissociation energy that is varies from 0 to 1.5, and that is highest for you can say for carbon fluorine bond, but relatively with respect to carbon iodine bond, that is the most easiest bond to break it down. So thus, in a way, this alpha carbon, if we wish to consider, then we can say that fluorine is a bad living group, chlorine will be a good living group than the fluorine, bromine is further good living group than fluorine and iodine. So this also can be given with respect to stability and basicity. Iodide ion is a good base, strong base, but as compared to this hydroxide ion, which is basically having this much decreasing basicity behavior. So basically, it wishes to say that poorest living groups are the strong base. So F minus, Cl minus, they are the poor living groups and they are a strong base. That is one of the reasons that the base living groups are the weakest bases. In other words, in a simple language, if I wish to explain, then fluorine is an atom which is having small size. So what will happen? The nucleus will have strong interaction with the electron which is present on outermost orbital. फ्लोरीन इसका साइज ही छोटा है, तो क्या होगा कि जो फ्लोरीन एटम है that will be interacting with the electron, the proton will be interacting with the electron very strongly. So that will not leave easily in case of fluorine. But as compared to fluorine, the chlorine is a bigger in size, 17 chlorine 35. That's why this chlorine has a big size, and maybe the interactions of this proton and electron is little weaker because of increase in size. ये interaction और भी कम हो जाएगा when we discuss this iodine. आयोडीन का साइज सबसे ज्यादा, प्रोटॉन का outermost electron के साथ जो interaction है, that will be the least interaction. So to avoid this interaction, generally we need to we need to break the bond. So carbon iodine bond is easy to break, and that's why iodine will behave as a good living group. The size, the basicity, this also matters when it will be considered. So SN2 reactions, basically, as you can see on the slide, that it is nucleophilic substitution reaction. However, the reaction happens to be second order. Second order means basically two substrates are involved. One substrate can be OH minus, another substrate can be alkyl. As you can see from this slide, that OH minus with its negatively charged hydroxide ion that is attacking on this carbon, I will say electropositive carbon, and thus it forms this transition state. So next is a removal of Br minus, and that will form this product. We have formed the product, this butyl bromide from butanol from this, let us say methanol from methyl bromide. So there are majorly 4 factors which affect the substitution reaction. So in this session, we are going to study all these 4 factors affecting the rate of the reactions. The nature of the substance, that means the nature of alkyl halide. The power of nucleophile, how that is the second most factor. And what is the capacity, what is the strong behavior of nucleophile, whether the nucleophile is strong or weak. So that we can study in this second factor. The third factor we are going to learn, that is the ability of the living group. What is the ability of the living group? Whether it is easily living or not living at all or moderately living. So these all factors are studied under the ability of the living group. Fourth and the last most factor, what is called the nature of solvent. In which reaction medium we are performing our reaction. So that is also important. The rate of SN2 reaction also depends upon this nature of the solvent. The vehicle, the reaction medium in which we wish to perform our reaction. For this, what are the factors? So let us start learning them one by one. Already it covers the power or strength of nucleophile, the strength of alkyl halide, the nature of living group, and the solvent which we are going to perform this reaction. These are the four major facts. Based upon this, the reaction can be possible. Consider the first one is the nature of substrate. What is the substrate in substitution reaction? The substrate is alkyl halide. So alkyl halide, basically it can be methyl, simply methyl bromide, methyl iodide, methyl halide, methyl fluoride. So all they are basically methyl halides. This is basically primary, secondary, and tertiary. That halogen containing carbon, if it is attached to only one carbon, so that is termed as primary alkyl. Halogen containing carbon, if it is attached to two carbon groups, so it is termed as secondary. Halogen containing carbon is attached to three alkyl groups, then it is termed as tertiary. So if our alkyl halide is methyl, then this reaction is fastest with methyl. Then it comes to primary, then it comes to secondary, and the list is with this tertiary. Now let me explain this, that why the reaction is faster, SN2 reaction is faster with this, let us say, I will say SN2 reaction is faster with this methyl Bhavan, and the rate of the reaction is poor with this tertiary butyl or tertiary alkyl halide. The examples are in front of you. Methyl, where halogen containing carbon is attached with only hydrogens, 3 hydrogens, I will say. Ethyl bromide, this one, where bromine is attached with a carbon, and that carbon is further attached with only one carbon. This is a one where bromine is attached with a carbon, and that carbon is further connected with two carbons, both methyl group. And the IUPAC name of the substance is isopropyl. Last one, where bromine containing carbon is further attached with a carbon, and that is basically total 3 carbons. So that's why this is tertiary. This happens to be secondary. Methyl bromide happens to be primary, and methyl bromide belongs to this methyl alkyl. So what happens that if we move from methyl to primary to secondary to tertiary, then their size increases. You can see here it was only methyl, now it is ethyl, now it is isopropyl, now it is tertiary. 4 carbon containing. So now here this basically alkane, and you can see all the yellow sphere which is in the structure, so that is basically bromine, and these are the 3-dimensional surface or ball model for these substances. This is only black portion is a carbon and white portion is a hydrogen. PR is yellowish in color. So here it is 2 carbons are there. Here there are isopropyl group is there. This is tertiary butyl. So what happens in SN2 reaction? If we let us just move a previous slide. So in SN2 reaction, OH minus is going to attack from the opposite side of the living group. This is the factor number 1, which is going to control the rate of the reaction. Now look at to this. In this reaction, if Br1, our nucleophile wish to attack, so that is open space to attack on methyl bromide. Here, for ethyl bromide, this space is little crowded as compared to this. Now look at to this tertiary butyl bromide. This is a bromine, and nucleophile wish to attack from this direction. If we wish to attack from this direction, then this position is further bulkier, sterically demanding in case of isopropyl. And if we wish to attack from this one, then this is going to attack from this side. So basically, tertiary butyl bromide का जो this है ना further that becomes crowded. Okay, so we were discussing that basically for ethyl bromide, if we wish to attack, then the position for this attack may be little uh, easier as compared to isopropyl bromide and tertiary butyl bromide, where generally the attack becomes more difficult for tertiary butyl bromide. So that basically we wish to say for this one. Now, next is what is the effect of nucleophilic this reaction on SN2? So, friends, let me explain here that this is basically this kind of. So, hopefully, here you may be clear that the rate of the reaction is that is inferior with respect to this tertiary, but that's the same rate of the reaction is faster when we go for, let us say, this SN2 reaction with this. So now next is this SN2 reaction that is practically not possible with methyl bromide and bromobenzene. So let me tell you why this reaction is not possible with vinyl bromide and bromobenzene. And when let us say a nucleophile which wish to attack from bromine, so basically this is a carbon where it's going to attack. What will happen? Nucleophile will have certain electron cloud. So this electron cloud is going to have a fighting with that electron cloud which is present as a p orbital of vinyl bromide. So that's why there will be a clash between the electron cloud of nucleophile and the electron cloud of vinyl bromide. Because in SN2 reaction, nucleophile is always going to attack from the opposite side of the living group. जहां से निकलने वाला है उसके ही opposite side पे file is going to attack in SN2 reaction. So this generally happens with SN2, and with bromobenzene I would like to say why this reaction is similarly not possible with bromobenzene, because when nucleophile will attack, so here there will be not only one pi cloud, but there will be, let us say, the 6 pi clouds or a complete circular pi cloud created with the help of pi benzene ring, which consists of pi cloud. So that's why this reaction is similarly not possible, because यहाँ पर भी there is a fighting between the electron cloud of nucleophile and the pi cloud of this benzene. इसीलिए SN2 reaction is only specific for alkyl halides, because alkyl halides are those substances they do not possess this pi cloud, which is found present in case of alkenes and benzenes. So that's why these reactions, SN2 reactions, are not easier as compared to alkyl. So we were discussing about this consideration of the power of the nucleophile, the effect of the nature, and with respect to this, this is basically going to affect the reaction. So we have to see that what are the nature of the nucleophile. So the second most factor after the nature of alkyl halide, the second most factor is the nature of this nucleophile. So what is this nature? Here we have to study this nature with respect to several terms are there, such as very weak, fair, good, and very good. So you can see that these are the different nucleophiles: HSO4, H2, SPO4 minus, RCOOH, ROH, F minus, O minus, CN minus, thiolatonines, etc. So to look at to this one, when the reactivity is very weak, so the rate of the reaction, relative rate of the reaction is much weaker in this position. But when it becomes to very weak, then literally it is higher. For fair, such as for F minus, this rate of the reaction is 500, and for good nucleophile such as Br minus or OH minus, so here it is the rate is drastically high. And for the very good reactive nucleophile, basically strong base, you can see triphenyl phosphine amide ion H minus and iodide minus, where this rate of the reaction is topmost, even more than 10⁸. So as we go down from very weak base or very weak nucleophile to very good nucleophile, the strong nucleophile, the rate of the reaction increases. So that is why that generally this rate of the reaction is dependent upon the concentration of the nucleophile. As the concentration of nucleophile increases, the rate of the reaction also increases. Secondly, this rate of the reaction also depends on the nature. That if it is a strong base, rate of the reaction is faster. If it is a weak base, rate of the reaction will be slower. So that is the basic fact we generally wish to study with the help of this. The third most factor we are going to learn, that is the nature of the living. Let me tell you that living group is one of the substance which is going to depart from the reaction. ये ऐसा substance है ना जो आपके reactant में पहले था, reaction के time में है, product में नहीं है. So that is going to live as a this thing. Okay, so this living group has certain tendency that whatever the living group after that, that should be enough stable. If it is not stable, then it will not able to join. It will not be able to meet the conditions. Just like शादी के बाद दुल्हन होती है, वो अपना पिता अपने माँ बाप का घर छोड़ के अपने हस्बैंड के घर जाती है. So that is also a kind of a relationship of living. Now, if she is not happy with her husband, so what will do? She will not. If she will not be happy, if she is not happy, then she may abandon her husband. वो अपने husband को छोड़ के वापस आ जाएगी. So living group is also like after departure from the substrate, if the living group is stable, then it is okay because it is stable. But if it is not stable and unstable, तो क्या होगा? Again, it will rejoin the family of the parents, just like the newly married is dulhan, or the people are marrying like if they are happy with each other, they will go ahead for their life. If not, then they may identify some other partners. So living group के साथ भी ऐसा ही है. If the living group after departure, if it is stable, then it will allow the reaction to continue. If it is not stable, then it will rejoin the alkyl halide and reversible reaction may occur. So here also why I wish to discuss that living group कैसे stable है. So how do we know that? हमें कैसे पता लगेगा कि living group stable है? Question is that, so basically let us say iodide ion. So iodide ion is more stable among all these Br minus, Cl minus, Pf minus, OH minus. Not only it is having highest pKb value, but also the rate of the reaction is faster as compared to NH2 minus, amide anion, alkoxide anion, hydroxide anion. So why iodide ion is a good living group? क्योंकि वो सबसे ज्यादा स्टेबल है. कैसे? क्योंकि उसका साइज सबसे ज्यादा है. साइज सबसे ज्यादा है तो क्या होगा कि वो अपने पास इलेक्ट्रॉन रख पाएगा. आयोडीन का साइज है ना, दैट इज फॉर मोर देन फ्लोरीन than chlorine. Fluorine is having, let us say, only 9 is the atomic number. This is having 7 or 17. Maybe this is having 35, and iodine is beyond than highest atomic number among all the halogens. जिसका दिल बड़ा है ना, वो औरों को भी अपने पास समा सकेगा. जिसका साइज सबसे ज्यादा है, जिसका दिल ही बड़ा है, वो सब लोगों को एक साथ अपने अंदर ले ले. पर जिसका दिल ही छोटा है, कंजूस आदमी है, तो वो किसी को एक पैसा भी नहीं खर्चा करेगा अपने दोस्तों के लिए या फ्रेंड्स और फैमिली. तो आयोडीन है ना, आयोडीन इज अ जनरस एटम. वो दिलदार और आदमी है, जो भी आया उसको अंदर समा लेता है, बिकॉज उसका दिल बड़ा है, उसका साइज बड़ा है. इसीलिए आयोडीन इज मोस्ट स्टेबल. बट जो फ्लोरीन है ना वो कंजूस आदमी है. 9 is the atomic number for fluorine. And basically इसका दिल भी छोटा है, साइज भी छोटा है, so that will not easily be stable. जो आउटर मोस्ट इलेक्ट्रॉन होगा F माइनस, उसको जकड़ के रखेगा, जाने नहीं देगा. If the parents are more strict than students, what will happen? That वो parents के against जाएंगे. Parents are not strict and हाँ चलो अभी तो चलो, now she is or he is mature, so let her live her life. Then maybe the kids will be able to learn the things better rather than a rigid or strict manner. Fine. So that basically concept over here is also there, that iodine का size सबसे बड़ा है, इसलिए it happens to be a good living group, and also it occupies the lone pair very easily. So that's why it is a non-basic one as well. जबकि OH minus is a poor living group. Why? Because it is a hydroxide ion that happens to be a strong base, and strong base always they do not leave easily, cannot be leave easily. So iodine है ना, वो will be happy even with after marriage, you can say, but OH minus will not be happy after departure of the parents' house. So that way, nature of the living group can be classified easily. Simple fundamental है कि after departure, if the living group is stable, then we'll be happy to leave the alkyl halide. If it is unstable, so it will not be happy. So again, we'll rejoin the hydroxide or this alkyl halide. Iodide happens to be a bigger in size, so that easily leaves and becomes stable. Hydroxide ion is not that much stable one, because after departure, it becomes unstable and being a strong base. So that's why it will not make the reaction faster. Okay, so in one message, that if we move from amide ion to alkoxide to hydroxide to fluoride, the rate of the reaction slowly progresses as we move towards chloride, bromine, and so that is the message of this slide. Now the last factor we are going to study for this factor affecting SN2 reaction, nucleophilic bimolecular substitution reaction, is the nature of solvent. Why nature of solvent is more important? आपने कहानी तो सुनी होगी, ठीक है, कि दो पैरेट थे, दोनों ही एक ही माँ बाप की संतान थे, पर जब वो आगे बड़े होते हैं, जब एक पैरेट है वो किसी पंडित के घर जाता है, दूसरा जो है वो किसी कसाई के घर जाता है. तो पंडित के यहाँ पे जो पैरेट बड़ा हुआ होता है ना, वो संस्कृत के श्लोक बोलता है, स्टांजास बोलने लगता है, एटसेट्रा. उसका वो पंडित की तरह बोलने लगता है. लेकिन जो कसाई के घर पे जो पैरेट गया है, जो वहां पे बड़ा हुआ है, वो पैरेट आगे चल के गालियां बोलने लगता है, और its language is not good, so maybe because of the this bad company. So man is known by the company he keeps. Similarly, if we wish to identify our nature, we can recognize the nature of ourselves looking at the nature of your friends. आपके दोस्त कैसे है वो पता लग जाए, तो ये भी पता लग सकता है कि आपका नेचर क्या है. आपके दोस्त ही बैड कंपनी है, तो नेचुरली यू आल्सो बिलोंग्स टू बैड कंपनी. इफ योर फ्रेंड्स आर बिलोंग्स टू गुड वन, you can also have a good moral character as well. Solvent के साथ भी, if the same concept is applicable to human beings, the molecules also follow the same principle. Our body is also made up of many molecules, so molecules are also following this similar principle. For SN2 reaction, this solvent happens to be the environment. जैसे वो पैरेट के लिए पंडित और दूसरे पैरेट के लिए कसाई. So environment is really a factor. So solvent, the reaction medium, the vehicle, happens to be such kind of this environment for the reaction. Now let me tell you how this is possible. Solvents are classified into different types: protic solvent and aprotic solvent. पहले तो solvent के दो टाइप होते हैं, polar solvent and non-polar solvent. पोलर मीन्स जहां जिनके अंदर पोलर फंक्शनल ग्रुप है, नॉन पोलर जिसके अंदर नॉन पोलर कोई भी फंक्शनल ग्रुप नहीं है। जैसे कि हाइड्रोकार्बन्स, मीथेन, हाइड्रोकार्बन सच एज टोल्यूइन, बेंजीन एटसेट्रा, दीज आर नॉन पोलर सॉल्वेंट्स, क्योंकि उसमें कोई पोलैरिटी है ही नहीं, उसमें पोलर फंक्शनल ग्रुप है। एंड पोलर सॉल्वेंट्स बेसिकली polar protic solvent and polar aprotic solvents are the types of such solvent. So जहां पे कोई ना कोई पोलर फंक्शनल ग्रुप प्रेजेंट रहता है, जैसे कि हाइड्रोक्सी हो गया, NH2 हो गया, कभी कभी सम DMSO हो गया. So they possess some polarity because of the polar functional groups. SH है, so these are basically polar functional groups. So protic solvents, we can consider that OH and NH2, just like water. You can see here examples are already there. Water, methanol, ethanol, acetic acid, they are polar protic solvents. क्यों? क्योंकि वो डिसोसिएशन करके H+ रिलीज करते हैं. वाटर का डिसोसिएशन करो तो H+ एंड OH-. मिथेनॉल को डिसोसिएट करो तो मिथॉक्साइड एंड H+. इथेनॉल को डिसोसिएट करो तो इथॉक्साइड and H+. एसिटिक एसिड को डिसोसिएट करो तो एसीटेट, anion and H+. So all these solvents are going to release H+ ion. H+ ion रिलीज करते हैं ना, इसीलिए उसको प्रोटीक बोलते हैं. आपको याद हो तो H+ को प्रोटॉन बोला जाता है, इसीलिए, क्योंकि प्रोटॉन इसलिए क्योंकि H+ के जो न्यूक्लियस है उसके अंदर एक ही प्रोटॉन होता है, न्यूट्रॉन नहीं होता है, इलेक्ट्रॉन भी नहीं होता है. That's why these are termed as, because of they, since they release the H+, that's why they are termed as protic solvents. Next is polar aprotic solvent, such as the examples are there in front of your slides. Dimethyl formamide, dimethyl sulfoxide, this is HMPA, hexamethyl phosphoramide, and dimethyl acetamide. These are the proton, these are the solvents, they are protic solvents. Sorry, they are polar solvent, क्योंकि उनमें पोलर फंक्शनल ग्रुप है. देखो इसमें अमाइड है, इसमें सल्फोन है, इसमें फॉस्फोरामाइड है, यहाँ पे अमाइड है. सो दे possess polar functional groups. मेजॉरिटी अमाइड है, सल्फोन है, फॉस्फोरामाइड है. So that's, but they do not release H+ ion. इसमें से कहीं से भी H+ ion रिलीज नहीं हो सकता है. इसलिए वाले वाटर, इथेनॉल और एसिटिक एसिड में रिलीज हो सकता है, यहाँ पे नहीं हो सकता, रिलीज नहीं हो सकता है, इसीलिए इनको बोला जाता है पोलर. पोलर तो है बिकॉज दे पोजेस पोलर फंक्शनल ग्रुप, एंड एप्रोटिक क्योंकि वो प्रोटॉन रिलीज नहीं करते हैं. Since they are not going to release the proton, that's why they are polar aprotic solvent. And non-polar solvents, such just like benzene, कोई functional group नहीं है, ना OH है, ना SH है, ना NH2 है. C6H6, carbon tetrachloride, CCl4, and hexane, N-hexane. So these are all non-polar solvents. उसमें कोई भी polar functional group नहीं. Friends, now this reaction of SN2 require the rate of the reaction is faster with, I will say, polar protic solvent or polar aprotic solvent. So this reaction is faster with polar aprotic solvent. क्यों? क्योंकि ये आप थोड़े पेजेस रिवर्स जाओगे तो ये जो रिएक्शन है ना, उसमें देखो कोई, आप ये जो ट्रांजिशन स्टेट है वहां पर कोई भी, आई विल से, देयर इज नो काइंड ऑफ एनी फोर्स आर इन्वॉल्व. I mean, forces तो है, but there is no involvement of charges. कोई कार्बोकैटायन नहीं बनता है, कोई कार्बन आयन नहीं बनता है, बस जैसे एक ने अटैक किया दूसरा भाग गया, ये रिएक्शन है. OH- का इस साइड से अटैक होता है तो Br- भाग जाता है. This is only one step reaction. There is no involvement of any carbocation, carbon ion. तो इसीलिए this reaction is faster with, जी का ऐसे कैसा प्रिंसिपल है ना कि like dissolves like. So जैसा होता है उसको वैसा ही पाता है. So this polar protic solvent, basically dimethyl sulfoxide, dimethyl formamide, acetonitrile, and dimethyl फॉस्फामाइड के अंदर ये रिएक्शन फास्टर है। एक एग्जांपल इसलिए है क्योंकि ये हाइड्रोजन बॉन्ड भी बनाना चाहते हैं। These solvents can easily make hydrogen bond with the nucleophile of SN2 reaction. That's why this reaction is always faster when we are going to deal with. So this is all what we learned today. In one slide, it is mentioned that SN2 reactions is faster with methyl than primary, secondary, and tertiary. Nucleophile, basically strong nucleophile, increase the rate of the reaction, and poor nucleophile decreases the rate of the reaction. Living group, if the living group is stable enough, it will increase the rate of the reaction. If it is unstable, it will decrease the rate of the reaction. And for solvent, it needs to be polar aprotic solvent to enhance the rate of the reaction. So this is the major concept we wish to study for this session. So we'll stop up to this and we'll continue our discussion from this onwards in the coming series. Okay, thank you.